Okay, example 7, differentiate y equals 3x plus 2 to the 4th times x squared plus 2x plus 3 to the 6th. Now, back in chapter 3.4 when we saw a structure similar to this, it was like square and maybe first power, and we actually multiplied it out just to make this nice polynomial that we just use the power rule for each one. When you start getting powers like the 4 and the 6, and especially a trinomial to the 6th power, that's going to be a bunch of terms. Maybe, that's going to be 5 terms there. This is going to be, I don't even know how many terms, maybe 13 terms. If you have 5 terms and 13 terms, I don't know, maybe 17, 18 terms altogether. It's going to make this a really long polynomial function if you try and multiply it out. It wouldn't be very pleasant to do. So the chain rule is our option here. But if you look at the structure of the problem, again, every time you do this and you're going to differentiate, you have to ask yourself, what structure is the problem? What rule do I have to use to differentiate this thing? I think we can all see this is a power function, right? 3x plus 2 to the 4th power. That's pretty much like the problem we saw yesterday. This is also a power function. All right? So pretty much like the problem we saw yesterday. The fact we're multiplying 2 power functions together, though, makes the overall problem a product of 2 functions of x. That's a function of x being multiplied by a function of x, right? So the overall problem to differentiate, I need to use the product rule. The product rule 1d2 plus 2d1, right? This is function 1, this is function 2. When I go to do d2 and d1, I'm differentiating a composite function, so I need to use the chain rule to differentiate. All right, so again, the overall problem itself here is a product rule. So I'm going to do the 1d2 plus 2d1, but when I do d2 and d1, I'm differentiating the problems like we saw yesterday, so I have to use the chain rule to differentiate. All right? So that 30 seconds of thought that we just went through is necessary in these problems. When you're doing your homework, go through that 30 seconds of thought and really focus on structure, and then by the time you get to the quiz, you only need about 10 to 15 seconds of thought to get to that same point because you practiced it and you got good at it. All right, I'm going to differentiate right away because, again, there's no way to algebraically simplify that within reason to make it a simpler problem. So I'm going to go straight to the calculus. I'm going to go straight to the product rule to differentiate this thing. 1d2, 1 means we write down function 1 exactly as it is. Nothing weird happens to it. It's just whatever it is. And 3x plus 2 to the 4th is what function 1 is. When I go d2, d2 is going to be the power structure, so 6 times x squared plus 2x plus 3 to the 5th. And that's going to be multiplied by 2x plus 2. Everything in red there is just the chain rule on the yellow highlighted function. 6 times base to the 5th, basic power rule of differentiation, multiplied by the derivative of x squared plus 2x plus 3, which is 2x plus 2. This is a basic function in here, x squared plus 2x plus 3. That's a basic derivative. Once you get to the basic level of this, you're done chaining. And then when I go plus 2d1 plus 2 is going to be function 2 exactly as is, x squared plus 2x plus 6, or plus 3 to the 6th. And then when I go d1, it's going to be the derivative of this thing, which again is a power structure, so I'm going to take the power rule, so 4 times 3x plus 2 to the 3rd, times the derivative of 3x plus 2, which is 3. Again, as you have to take a derivative, what rule do I have to use to differentiate? In each case, the derivative of this is chain rule, derivative of this is chain rule. Okay, this is another basic structure that you're going to see quite often in this section, and also it's going to happen on quiz and possibly test. Polynomial to the power times polynomial to the power, the product rule to differentiate, chain rule within it. Here's something that happens every time on these problems. 3x plus 2 to a power, 3x plus 2 to a power. X squared plus 2x plus 3 to a power, x squared plus 2x plus 3 to a power. That's not a coincidence, that's just a consequence of the structure of the problem. That's going to happen. Again, for the sake of elegance and also the sake of easiness on your part, we want to expect this type of stuff to happen, see how to handle it. So what I'm going to do here is what happens every time, 100% of the time, whatever the problem started off as. This always happens 100% of the time. Now I could have looked up here to establish a greatest common factor. I could have done that. But what always happens is whatever this problem is to begin with, you always get one less power for each of those things as a common factor. 4 and 6, 3 and 5. Whatever these powers are, drop one off. That's going to be the greatest common factor. If you want to verify that with what we actually have written here, this whole thing is term 1, this whole thing is term 2, right? 3x plus 2's, we have a 4 and a 3. We're allowed to take the smallest power out that's common, right? So 3x plus 2 is common. 3 and 4 are the powers, the smallest power is 3. X squared plus 2x plus 3 is common. 5 and 6 are the powers, smallest power is 5. That always happens. The reason it always happens, when I do D2, the power drops by 1, right? When I do D1, the power drops by 1. When I do 1, the power is whatever it was. When I do 2, the power is whatever it was. So the drop by 1 is always the smaller power. That's what's going to be the common factor every time. And it's not a coincidence, that's just what happens. If you are willing to do that, which hopefully you are because I'm expecting you to, otherwise you're not going to get full credit on this problem because there are so many different correct answers that are just ridiculously large to look at. I'm not going to focus on it. So you need to do it this way. Okay? If I take 3x plus 2 cubed out of 3x plus 2 to the fourth, what's left over?
3x plus 2.
3x plus 2 to the first, right? I didn't take anything out of the 6. If I take x squared plus 2x plus 3 to the fifth out of x squared plus 2x plus 3 to the fifth, what's left over? Nothing. And then I got a 2x plus 2. So out of this whole first object here, we're left with one of these because we took 3 of them out. This, we took all that out, and we're left with that. Right, so I'm just extracting a common factor. It's making each term simple to look at. If we take a look at the second one, let's use this color. Okay, so here's my second object. I'm taking x squared plus 2x plus 3 to the fifth out of x squared plus 2x plus 3 to the sixth, which makes x squared plus 2x plus 3 to the first. Taking nothing out of 4. I'm taking 3x plus 2 cubed out of 3x plus 2 cubed. That just goes away, and I've got a 3. All right. Looking at the bracket, this needs to be simplified now, but instead of having to take something to the fourth power, something to the fifth power, multiplying a bunch of stuff, we've taken all that stuff out. We're left with pretty simple, right? We got a FOIL times 6, and we got a 12 times a trinomial, so a distributive property. So let's FOIL first. I like to FOIL first because FOIL is the more challenging thing of the stuff, right? Times 6 is easy. So I'm going to have a 6 here, parentheses. 3x times 2x is 6x squared. 6x and 4x is 10x. 2 and 2 is 4. And here I've got 12 being multiplied by x squared plus 2x plus 3. Continuing on, if I multiply 6 through that parentheses, I get 36x squared plus 60x plus 24. If I multiply through that parentheses, I get 12x squared plus 2x plus 24x plus 36. 12 times x squared, 12 times 2x, and 12 times 3. And our final step of algebra, 36x squared plus 12x squared is 48x squared. 60x plus 24x is 84x. 24 plus 36 is 60. All that's being multiplied by 3x plus 2 to the third times x squared plus 2x plus 3 to the fifth. And that's what y prime is. I don't think it's necessary to keep bringing this stuff down each time. Just know it's part of the answer. Don't forget about it when you get done with all that stuff. The book is very fond of seeing that there's a common factor of 12 amongst these, and they pull a 12 out also. I don't see the need in doing that. So I like this completely simplified. Don't worry about common factors for that specifically. But I do want to get these powered common factors out because, again, it just makes the simplification of all this so much more easy. And again, it makes for a very elegant answer. There's only 3 components to it, so when I'm going to check your paper compared to what the correct answer is, it's very clear. This piece, this piece, this piece. It's quick to grade, quicker for you guys to do, so it's worth going to that effort to make that happen. All right, so again, that structure is going to work pretty much like that. One thing they might throw you for a curveball on these in the homework is they might throw a negative power on one of these. When you're looking at negative powers, let's say you have -2 and -3, right? Which one's smaller, -2 or -3?
-3.
-3. So you take the -3 out, and that leaves a first power on the -2 that's in your work. All right. That's the one weird thing they might throw at you on those. That's how you handle that situation.
So that's the answer.
Yeah, that's it. That's the best derivative of that, in my opinion, is that. Again, the only thing the book would have done differently than that, 48, 84, and 60 all divided by 12, they would have taken the 12 out. I don't see the need in doing that. I mean, yeah, it's a common factor, but I think that gives me 3 pieces to look at instead of 4 pieces. So,